All right, let's take a look at the 2016 E&M problem number 1. What they give us here is an unknown charge and a positive charge of 2 nanocoulombs on a Cartesian plane and some equipotential lines drawn around them. And remember, these equipotential lines are like a topographical map that shows elevation, except these elevations are measured in volts. The fact that the lines that are curving around the unknown are negative, and as you move away from this unknown charge it gets less negative, indicates that this is going to be a negative charge. So part A, calculate the value of Q1. Let's take a look at point B over here on the right. At point B, that's on the 0 volts equipotential line. So everywhere on that curve that's almost a circle, we're at 0 volts, essentially sea level. And if you move towards Q2, you're moving uphill. And if you move away from Q2, or if you go around the line to the other side and then move away from Q2, you're moving downhill. Looking for the value here, we can use voltage. So voltage from 1 plus voltage from 2 is going to be the voltage at point B. And the voltage at point B is 0. So V2 plus V1. Well, from a point charge, voltage is going to be K Q1 over R1. And then we'll have the same thing from, I went and switched these, from the other guy. And they add up to be the voltage at point B, which we've established based on the diagram is at 0 volts. So we can rearrange this because we're trying to solve for Q1. So our constant of the universe cancels out. And we're going to have Q2 over R2 equals minus Q1 over R1. Now let's figure out what R1 and R2 are based on our diagram. Our legend up here indicates that one of those dark bars is ½ a meter. So from Q2 over to B is 1 meter. So that guy is 1 meter. For 1, it's 0.51, 1.52, 2.5. So that guy is 2.5. So Q2, this is going to be 2 times 10 to the minus 9th over 1 equals minus Q1 over 2.5. Rearranging, well, we're going to cross multiply, so 2.5 times 2 is going to be 5.0 times 10 to the minus 9th coulombs, and then this minus sign has to come over, so we're going to have a minus 5. So Q1 is going to be twice as big and negative of Q2. All right. Point B, part B. Point C on the diagram. Well, let's blow this guy up. And here's point C. Point C on the diagram, and they want us to draw the electric field at that point. Okay, so the equipotential lines are like elevation for a topographical map, and if you walk along it, you're at the same elevation. The electric field is like gravity. Well, gravity is going to pull you perpendicular to that equipotential line. So the electric field is going to be perpendicular, and it's going to be one direction or another. And the electric field indicates the direction that a proton or a positive charge will naturally move in. And it's going to move from a positive voltage to a negative voltage, or to a more negative voltage. So since the C is on the 12 voltage line, the proton is going to be moving, and therefore the electric field points towards the more negative, and this guy is going to be perpendicular to the equipotential line. So the electric field is going to point down and to the left. All right, part C, calculate the approximate magnitude of the electric field at point D. So if we take a look at point D, here's point D. And we can calculate the approximate electric field using the distance and these two electric potential difference between those two lines that are the equipotential lines. All right, so what is that distance? Well, coming back to our legend here, this indicates that each minor tick mark is a 0.1. So this is 2 minor tick marks, which is a 0.2 distance. So let's get rid of those guys and shrink this down, and we'll go back to our writing pad. This guy was A. Now for C. The mathematical relationship between the electric field and potential difference is if you take the derivative of the potential difference with a minus sign to indicate the electric field is pointing downhill, you're going to get the electric field. Well, in this case, from C, we're going to have minus, and then minus 24 minus negative 20. And then the distance is a 0.2. So this is a difference of 4 over 0.2, which gets us 20 volts per meter, and it points almost nearly straight down. Now, if we come back here to part C, it says magnitude. So since they say magnitude, we don't actually even need the word down. What we need is just that 20, and then your units. And your units for electric field are either going to be volts per meter, because if you keep in mind here, that's volts, and the distance that we just measured is meters, or you can use newtons per coulomb. Either one of those is acceptable. All right, part D. The equipotential labeled 0, that's around point B that I used before. Calculate the electric flux. Okay, the electric flux is caused by charge enclosed inside a surface. Well, what charge is enclosed by that circle, or almost circle at 0 volts? It's just Q2. So Q enclosed is just Q2. And if you notice here, doing your work for part D does not depend on correctly calculating way back in part A. These parts are independent of each other. Now, this E epsilon naught is a constant of the universe that we discussed in class, and you can look that up, 8.85 times 10 to the negative 12th, and that is going to be our flux. Plug these guys into your calculator. Keep in mind that nano is times 10 to the minus 9th, and your calculator should spit out 226. 2 divided by 8.85 is approximately 226. And then we have 10 to the minus 9th over 10 to the minus 12th, and that's how we end up in the hundreds. Now the units here. We're talking about flux. If you remember from Gauss's law, the other side of the equation was electric field times area. And yeah, I know I had this funky calculus symbol stuff, but the units is what we're interested in here. Electric field, remember, that's newtons per coulomb, and area is meters squared. It doesn't matter if we're on the left side of the equation or the right side of the equation. Once we're all done, all the units have to be equal and the same. So newtons per coulomb times meters squared is going to be our units for the flux. Now for parts E and F, I'm going to have to do some more calculations, so I'm going to pause here for a moment and clear out my writing pad. Part E is that we're going to put a proton at point A, and we're going to let it go from point A to point E, and point E is over here. So here's point E, here's point A, and it's going to go from A to E. So it's going to go from the plus 4 volts to minus 4 volts. It's essentially going to be rolling downhill. You could think of putting a bowling ball on a smooth mountain and letting it go and watching that it goes down the hill towards the valley. So for E part I, the work is going to be the same thing as change in energy except with a minus sign. So we're going to have minus Q change in voltage. Now it's going to be losing voltage, and that's where this minus sign comes in. So we're going to have the charge on the proton, which is 1.6 times 10 to the minus 19th. And the change in energy is going to be 8 volts because we're going from a plus 4 to a minus 4. And the fact that it's going downhill means this is a minus 8, but we have a minus here also. And those two minuses cancel each other out. And when you plug those two numbers into your calculator, 1.28 times 10 to the minus 18th joules. A natural follow-up to that is, well, how fast is it going? Which is part 2. How fast is it going when it gets to point E? Well, work is also change in kinetic energy. Well, we just found out what the work is. That's our answer to part 1. And change in kinetic energy is going to be 1/2 mvf squared minus 1/2 mv naught squared. And we look back here and we say, oh good, it was released from rest. So v naught squared is 0. All right, mass of a proton, that's another number that you can look up, or you might accidentally have it memorized. 1.67 times 10 to the minus 27th kilograms. So we're going to equate the work done by the electric field with the kinetic energy. And we're going to use that to solve for the speed. Keep in mind, this V is speed, it's not voltage. I've been trying to write it as a lowercase v, and the voltage up top is a capital V. Plugging these into your calculator, rearranging, solving for velocity, don't forget to take the square root. You should end up with a reasonably large number in human terms for how fast we're going, 39,000 meters per second. All right, part F. Now, instead of a proton, you need to keep in mind here, part E was about a proton. Part F is about an electron. And the electron we're going to put at point B. Well, if the proton naturally will move from A to E when we let it go, the electron is going to move in the opposite direction. It's naturally going to move towards the positive charge, because remember, opposites attract. So if we release it from point B, the initial motion is going to be the left, and electrons fall towards positive charges. Positive charge here is Q2, and the electron is going to be pulled towards the positive charge.